I thought what we might do the next couple of weeks was delve into using the Gaussian mixture model stuff to look at particle variability, not just because of the Gaussian mixture model material, the program itself, but also because that was a good mechanism to sort of force us to look at file formats and delve into how deep learning software might integrate with EMAN2. So my thought was today we might start out with a data set, someone else's data set that they'd processed and put in Empire, and today maybe target just sort of trying to get that data set ready for processing with the Gaussian mixture model next week. Then next week start doing some of the Gaussian mixture model stuff, and maybe continue with that the following week. That's the order of things that I suggested. So I don't know if any of the rest of you managed to download this this Empire entry I talked about, or even tried. Downloading Empire data, if you haven't done it before, can be a kind of painful and frustrating process sometimes. Either they want you to use their Globus interface, which a lot of sites don't have access to, or they want you to use Aspera, which is this plugin which only works on certain computers some of the time and sometimes gets blocked by people's firewalls. And then the only other option is basically to download using HTTP, and they massively limit the bandwidth of that. So downloading even a small data set can take days when you do it that way. Anyway, I managed to download this data set. My plan is we'll do a lot of the pre-processing and stuff today, and then I'll take the final result of that pre-processing, which should actually be a little smaller, and I'll put that on a server here that people who are participating can download before we try and tackle the GMM stuff next week. I'm not saying you can't download it yourself and then do everything we're doing today. You're more than welcome to do it that way. But if you find that Empire download process frustrating, we can have this alternative. All right, so the data set that I was thinking we would look at here is, yeah, you can see I was looking up zip bombs because it was complaining that the Empire data set that I was looking at was a zip bomb. It wasn't, but let's see. Zip bomb is a maliciously constructed zip file which can be used to disable the antivirus system on a computer by making it use too many resources or something. I don't think it's really a very common thing anymore. The reason I think it thought it was a zip bomb was because the zip archive had something like 15,000 files in it, and that makes the zip software suspicious. So you have to disable the unzipping software, disable the zip bomb detection in the unzipping software before you can open it. Anyway, these are just some of the things that you'll run into when you try and download data. Okay, so the Empire data set that we're working with here is 11005. I have not ever tried this data set before. I picked it kind of randomly because it's a data set that provides boxed out particle data, not just the raw micrographs. A lot of people, when they upload stuff to Empire, feel like they're forced to upload stuff to Empire, and don't really want to make it too easy for anyone else to do stuff with their data. So they kind of upload stuff in a not always very convenient format. At least I think that's what's behind it. There's only some groups that will sort of really try and upload not only the raw data, but also the boxed out particles in the star file that they got from their Relion or their CryoSpark refinements and whatever. So this was an example of the data set where they provided both the raw micrographs as well as two subsets of the particle data, which had been classified into an open state and a closed state. And my thought was that we would mix these two data sets. I mean, they're significantly different in size. This is only 57,000, 364,000. But anyway, that we might mix these two data sets together and then try running the Gaussian mixture model stuff on it. Again, I've never done it on this data set before. It may not do anything very useful. I suspect it'll probably give us something at least. I mean, we should at least be able to kind of resolve these two classes from it. But anyway, this is the data set I picked. Now, the overall data set is 1.1 terabytes, but that includes the raw micrographs. If you look at the size of the data from the particles, they're a lot smaller, right? So the small particle data set's 27 gigabytes, and the larger data set's 176 gigabytes. So still a good chunk of data, but not over a terabyte. So I actually downloaded everything, but what I have here is just the open particle data set. So this is all of the files here except for the EMAN2 folder, which I'll talk about in a second. All of these files here came from Empire, from that Empire download. So this folder contains all of these image files, and each of these files represents the particles which were extracted from one micrograph, which were in the class of open state particles. So if we look, we can see there are 15,103 of those files, meaning that they started with 15,000 micrographs in this project. Right, how many particles does that represent? So we've got, we can see, oh yeah, here we go. So we can see that's 57,000 particles. So you can see 57,000 particles, 15,000 micrographs. That means they were really only getting a small handful of particles out of each micrograph. Now, most of that is probably because of this data set, which is much larger, this closed state data set that's presumably intermingled with the open state data set. And this is a much larger population, but even here, you're really only talking about getting something in the order of 10 or 15 particles out of each micrograph. I don't know. I haven't looked at the raw micrographs to see whether that just means the data was really sparse, or whether that means that when they pre-processed and did the early classification, that there was a lot of data they threw away. Now, if they threw away a lot of data, that would imply that probably if we want to do the GMM stuff, we should actually go back and kind of pick the particles ourselves. But I'm not sure if I want to tackle that for this group or not. Anyway, so we have the open particle data set, and I think we'll look at that one today. And then when I sort of pre-process the data that we'll use next week, I'll merge together the open data with some of the closed data, and I'll just give you a folder that you can download. Any questions about any of that? All right. So you can see all of these files are in the MRCS format. The S, on the MRCS, so there's no difference between an MRC file and an MRCS file. The S just denotes that the file is a stack file, meaning that it's not that it's stored as a 3D volume, but it's not really a 3D volume. It's really just a bunch of particles which are stacked up along the z-axis. That's just a naming convention that the field has sort of adopted. If we say e2 eminfo particles and just give it, and just give it one of those files, we can see, yeah, MRC format 360 by 360. And there was one particle in that file. So you can see the data is 28 gigabytes total. And we also have the star file associated with the data. If we do a WC on the star file, we won't get an exact count of particles because there's other stuff in the star file too, but we get a rough count of particles that way as well. The EMAN2 folder is a folder that I produced by processing importing the data into EMAN2, and we'll talk about that in a minute. But I will point out one useful thing, which is if we run that the EMAN2 representation of exactly the same data is only 7 gigabytes, not 28 gigabytes. So it's reduced in size by about a factor of 4. And that relates to the data compression paper that I emailed out in the link this morning that people look at. I'll point out that that link I sent out this morning to the paper is the sort of the early publication link, which you can download for free, even if your library doesn't subscribe to JSB or something like that, for the next 3 weeks or something like that. After 3 weeks from now, that you'll have to have JSB access to get that paper until it gets publicly released a year later, whatever the NIH policy is now. Okay. So star files. I'm guessing most of you are probably familiar with star files, but we can take a look at this one just to. Oops. So if we're talking about single particle analysis, there are a variety of different representations people use for both the data and the metadata associated with the particles. The interchange format that you'll find people using, and the format that works natively with Relion, is the MRC format for the image data. Now, the metadata is not generally stored in the MRC file format because the MRC file format has a fixed size header, and the stuff that fixed size header lets you store is not really very useful for the most part. So the metadata then gets stored in some other associated file, which will also usually sort of group together the data from many, many different micrographs. So if you have all the particles from one micrograph, or maybe multiple micrographs stacked together into a big MRCS file, then the metadata would be stored in one of these companion files. Now, if you're using Relion, the star file format is what's used for this representation. So just a little bit of history on sort of metadata in cryo-EM. So if you look back in the early days of the protein data bank, protein data bank files use these PDB files, PDB format files, which I probably have some here. Oops. We can just look at one. Which looks something like this. They're these human readable text files. Each entry exists on one line in the file. The beginning of each line indicates sort of what type of line it is, and then after that, all of the information on the line is in some sort of fixed format. Once you get down to the atom block, there's actual spaces in here. These aren't like tab characters or something like that. So all of these fields are fixed width. And the reason for this was basically the Fortran programming language and how Fortran had to deal with data coming out of files. Basically, it had to be in sort of fixed length records. So they defined exactly how long each line would be, and then Fortran would read in the line and then be able to parse out the data very precisely. It's a very archaic sort of thing, but the PDB file format, still remains in use now, even though it's been deprecated by the PDB itself as of a few years ago. But it has problems. So if you look at sort of like the atom number field, the atom number field there, there's only 5 characters allocated for the atom number field. There's only 5 characters allocated for the atom number field. So that means that if you have more than 99,999 atoms in your PDB file, you're stuck. You can't do it. You have to break your molecule up into multiple PDB files. And that was really sort of the straw that broke the camel's back and forced the PDB to come up with a better file format. Now, the programmers who dealt with PDB files were very resistant to change, and took them on the order of 20 years to get the X-ray crystallography community to really sort of agree to really finally shift to the new file format. And the new file format is basically in star format. They call it something else, but it's basically star format. If we look at one of these star files, they have certain similarities to the file we were just looking at. Basically, a star file is designed to store spreadsheet data, more or less. It's designed to store a block of data where you have rows and columns, and every row and every column has to be populated with values. But the individual rows and columns have sort of arbitrary width and more or less arbitrary contents. So the beginning of one of these files, there's this data block, then you'll have these loop blocks, and each loop block defines basically one table in a spreadsheet. You could have multiple loop blocks in one file, and then each loop block would be sort of a different spreadsheet, a different table in your spreadsheet file. So then the first thing that you have after the loop block is a definition of what all the column names are. And then the rows are just different elements in this sort of database that they're building up. So each column would contain a different type of data, and each row would be a different particle. So we start out with X coordinate, Y coordinate, psi. You can see all these things start with RLN because these are Relion defined. This is a Relion definition of this file format. You can also, if you're used to looking at these star files, you'll also note that this is a somewhat out of date Relion file. This isn't, modern Relion files will actually take some of the common parameters like the microscope voltage and some of that stuff, and they'll make a separate loop up at the top to contain that information, and then they can have fewer columns in the rest of the data, which makes the file substantially smaller. Anyway, so this is how Relion stores its metadata. Each particle is on one line, and each line basically has all the information that you might need to do your reconstruction and figure out all the parameters of the particle. EMAN, on the other hand, had historically used other approaches than this. The approach that has been used, 10 years ago, we were using something, this sort of BDB approach for storing things, which was this sort of local database format, and is actually one of the reasons why people switched from EMAN to Relion so heavily back 10 or 15 years ago, was because the annoyance of that strategy. So about 12 years ago, we switched from using that sort of database strategy to JSON files. Let's see. So if you look in an EMAN2 project, so this was a project, and I'll explain how we generated this. So if you import a Relion project into EMAN2, what you'll wind up with is a folder called particles and a folder called info. And the particles folder will have basically exactly what was in the other particles folder we looked at a minute ago, except instead of being MRCS files, they're HDF files. So HDF is the native file format that EMAN2 uses. And the info folder will contain all of the metadata on a per micrograph basis. And you can see this is, there's basically one of these JSON files for each micrograph. The other file format that you'll see being used sometimes in this field and other fields that the PDB also uses is XML. XML was designed to be a human readable format, but XML files are really long and convoluted, and they're annoying to read. JSON was a somewhat newer alternative to the XML file format, which is written in JavaScript. So if we look at one of these files, you can see it's human readable, and it looks kind of like a program, right? You've got the open curly braces, and then we've got CTF frame colon. So this is basically like a dictionary in Python. And then the CTF frame leads to a list, and the list contains another dictionary. Well, it contains a number, and then it contains another dictionary. The dictionary contains the CTF parameters. So this is a hierarchical file format. So you can store any sort of arbitrary information that you want in one of these JSON files, which is a real limitation of the star file format. The star file format, all of the information you store has to be tabular data. And that's fine for certain types of things, but there's certain types of metadata that you might want to store in a cryo-EM project, which you can't conveniently do. So let's maybe take a little aside and take a look at one of those. Oops. Sorry. Let me just go to one of our tutorial workshop data sets, and we can just look at that. Right. So this was a single particle refinement done in the canonical EMAN 2.9 and earlier way, where we have various refinement folders, and again we have a particles folder just like the one we have. We have the info folder. So this is kind of what an EMAN2 project looks like after you've run a bunch of different refinements. So lost track of what we were talking about. So we were talking about Json files and entries. Yeah, that's what I was doing. So let's run E2 display, and so the refinement strategy historically that EMAN2 has used has involved classifying the particles in 2D before doing the 3D reconstruction. So if we look inside one of these refinement folders, we'll find that there are these class average files, and you can see it's split into even and odd halves. So so these are all, whoa, sorry, that went a little too fast. So these are all class averages. You can see that there's some junk in some of the class averages and stuff, but here, for example, is a nice looking class average in a particular orientation for beta galactosidase. You can see there's a few other nice ones there. So one of the things that you might like to know is which particles went into that class average, right? If I double click on that in EMAN2, it'll open up another window for me, and I can immediately see the 3 particles which went into that particular class average, or the 8 particles that went into that particular class average. These aren't oriented; they're all in their original orientations. Now, how would you go about storing that information in the star file? Right, the information about which particles went into the class average. So the way you pretty much have to store that in a tabular form would be the other way around. Instead of saying, here's a class average, which particles went into it, you would have to say, okay, here's my list of particles, which class did each particle go into? So that's fine, it's the same information, but it means that if you wanted to extract this metadata about which particles went into this class average, you'd then have to go back through the database, which might have 1 million particles in it, and search every one of those 1 million particles to find the ones which were members of this class. So a little bit of programming effort and a little bit of time would be involved in doing that. It's very convenient if you can actually store the information about the classification associated with the particle itself. So if we look at the header of each of these class averages here, you can see that the header data includes things like, all right, let's see, there we go. Includes things like the indices, which particles which went into this particular class average. We will also have another field, or I guess there weren't any excluded here, but if there were particles that were excluded from the class, which were classified in this class but then excluded, there would be another metadata field which would contain the list of those. There weren't any in this case, so that's missing. I wonder if we'll see any in any of these others. So you can see the ones that are missing metadata entirely are the particles which, sorry, the class averages which didn't have any particles associated with them. Anyway, so this sort of flexibility is one of the reasons why we went that way with the Json file format. Now recently, with the pre-EMAN3, which we've been working on, we've actually taken another little shift. The JSON files are fine; they're human readable, but you kind of have to go into Python if you want to really sort of parse them out. And there are some complexities associated with that. Similar to the star files, there's no, let me go back here again. So let's take a look at the star file again really quickly. So the issue with the star file is while each line in the file here contains the same number of parameters, the line lengths are all over the place. So what that means is if you want to write a program to read the star file and you want to say read out the information about the 50,000th particle in the file, there's no good way of jumping immediately to the 50,000th line. You have to actually parse through the entire file until you get to line 50,000, and then you can read the parameter out. So most programs that do stuff with star files will actually read the entire star file into memory, and then you can sort of immediately jump to, so they reformat the information in the memory of the computer. But of course, then if you have, 2 million particles and you've got, 30 parameters for each particle, now you're talking about, like 100 megabytes occupied with just this, this star file representation. It's kind of obnoxious. So a similar sort of limitation exists with the JSON files. That the JSON file is sort of a representation of a dictionary, and you more or less read the entire JSON file into memory, and then you can parse out the information you want conveniently as if it were a Python dictionary. But there's no sort of convenient way of easily seeking around the file. So with the sort of this pre-release of EMAN2, we've now moved to a newer an old file format, which has been kind of repurposed again, which is the Lst file format, which dates back to EMAN1, which is kind of like the star file, but more flexible. So not sure if we have one yet here. No, probably not. Okay, so I probably actually should have started this a while ago. All right, so let's say we have this folder containing all the MRCS files, and we have our Relion star file here, and we want to get this into EMAN2. So there's been a program for the last 10 years or so called E2 Relion to EMAN. And you could run that on a star file, and it would create a folder called EMAN2, and that's exactly how I created this. If we say help here, you can see you basically just give it the name of the star file. And if you want to override any of the values in the star file, like the angstrom per pixel value or the voltage or something like that, there's a few other parameters you can specify, but otherwise it'll just read the star file and it will create this EMAN2 folder along with all the metadata and stuff. The trick about this program is it preserved information about the micrographs. It preserved the angstrom per pixel and the voltage and the C sub s and stuff like that, but it intentionally sort of discarded all of the orientation information that was present in the star file. So the idea would be if you wanted to re-refine your data set in EMAN2 for comparative purposes, you could run this program and you could make an EMAN2 project, and you could run an EMAN2 style refinement in that same project, starting from scratch with all the orientation parameters, and make sure you get the same result. What we're talking about today is trying to make use of a Relion refinement and the orientations from the Relion refinement to run one of these Gaussian mixture models to look at the variability among the data set. So in that case, we actually do want to preserve the Relion metadata. So there's another program which is stored in the EMAN2 examples folder right now. So I'm just getting this out of the source tree, but you'll also find this in the binary distributions, right? If you find the examples folder, there will be a bunch of programs in there which do various sorts of simple tasks. And there's an E2. Nope, E2. I have to remember the name of the program. E2 convert Relion. So we'll go ahead and run that program now. Okay, this is very similar to the other program. It just generates one of these new format LST file instead of generating the old format sort of JSON structure. So I'm going to go ahead and start that running now, because it's going to take a while to run, probably 20 minutes or something, because we're talking about 14,000 micrographs to deal with. So we just give it the name of the star file. And I don't think we have to give it anything else. I'll go ahead and say v1 for a little more verbosity, so we see what it's doing. And yeah, that's it.
Oh, Steve, can you tell me the star file, how many lines in it? I mean, I'm trying to get a feel for the numbers.
Oh, actually, it doesn't have a verbose option. Hang on a second. Yeah, I'll answer in a second.
Sure.
Okay, it doesn't have a verbose option. That's fine. Okay, so we've got this running, and now you can see. So what did you ask, Phil? How many?
How many lines? Yeah.
Well, so there were 57,000 particles in the file. So there are a few more lines than that, just because of the definitions of the columns.
Then why does it take so long? I was a little surprised.
Why does what take so long?
You said it would take 20 minutes to do something.
No, that's because it's also copying all of the data from MRC format to HDF format and compressing it.
Oh, I see. Oh, I see.
Yeah,
okay.
Yeah.
Okay,
if we tell it to skip the data copy, then you're right. It'll probably only take 10.
Okay, just trying to keep on top of all the points.
Yeah, no. I ask questions when you have them. I'm spewing out lots of random knowledge from 20 years. So, okay, so you can see this is running. It's going to take a little bit of a while to finish, but we can. Let's see. Let me see if I have an LST file from another project. All right, I have a GMM folder where I've done various GMM work in the past. Okay, we can look at this folder. So this was just some test run I was doing with the Gaussian mixture model on GrowYell. But you can see that there's a file called particles.lst in this folder. And the particles.lst file is this newer format that we're producing. And the idea is that, sort of like the star file, you will have one particle per line in this file. The difference is that the metadata that you can provide after that is then in basically a JSON-like format. So basically, you have the particle number and then the file name. And that's how LST files have always been formatted. Basically, an LST file was just sort of a way of virtually grouping together a bunch of particles that were in multiple files into a single file without having to copy them. So if I run E2 display here, it sees that particles.lst file as an image stack file, even though really it's just a text file. Okay, so EMAN treats these LST files as if they contained actual images, even though what they contain, even though really they're just text files which contain references to images. Now, in the old days, basically all the file would have would be this: number, file name, et cetera, et cetera. This is sort of the new extension. Now, the file format always permitted us to do this sort of thing, that you could have sort of this comment available after that, but we're now using this to contain metadata. So basically, each particle in the HDF file has header information associated with it. So let me do that. So let's look at the HDF file. So the HDF file has 5,000 particles. If I hit info, I can then look at the header information associated with any one of these particles, right? So here's all the header data stored about that particle. And it includes sort of standard parameters up here. You can see that this data was actually compressed. These render bits, render max, render min, truncated. This stuff is all associated with that paper that I passed around in talking about how many bits were preserved in the header of the data. But if we think about storing information about, say, the particle orientation along with the header of each particle, we could do that. You know, we could take particles.hdf and we could store the particle orientation and the defocus and all that stuff directly in the header of the image. But that would mean that every time we ran a refinement, it would be modifying the data in the header. And if we wanted to make, you know, if we wanted to run a refinement and then we wanted to run another refinement, we'd have to make a copy of all of the data in additional to the metadata to alter those header values, because you know, it's one header, you can only have one set of values. So that's you know, the header is a great place to store fixed data that's never going to change, but the header isn't really a very good place to store data which you're going to be determining maybe multiple times and that sort of thing. So this LST format allows us to reference the image data in one of these files and also reference the header data in those files. But then any information that you provide here can override the information that exists in the header. So if there were a transform.projection, oops, shouldn't have dragged. So if there were a transform.projection header value present in the particles.hdf, if I read from the LST file, the transform.projection value that I saw would be the value from the LST file instead of the value from the HDF file. So I can then make as many of these LST files as I want, and each of the LST files will contain any of the changed metadata about the particles. The other useful thing about these LST files is that they're formatted in such a way that every line in the file has exactly the same number of characters in it. It's not a fixed number of characters. Each file can be a different number, but in this case, it's 193. So basically, you have these comment lines at the beginning. Then there's a line here which says how many characters are going to be in every line in the rest of the file. And what that allows you to do as a programmer is immediately seek to particular particle within the file. And it makes reading and writing these text files directly from disk feasible and very quick. So even if you had a file that had 10 million particles in it, you could immediately seek to particle number 5 million and read the information out of it. Now, from a programming perspective, all of these different types of metadata files, the star files, the JSON files, the LST files, can be conveniently parsed and handled using Pythonic sorts of approaches. So if I run, we'll go ahead and look at an LST file here. An LST file, as I said, you can treat immediately as an image file in EMAN2. So I can say, let's see, I'm say A equals em data particles.hdf, and we'll read the 10th particle. And we'll say B is equal to em data particles.lst, and read the 10th particle from there. And these two files, the image data for these two will be exactly identical. But if we look at the metadata associated with the file, we'll see that the transform.projection here associated with the it looks like I actually this is actually a bad example because it looks like we actually may have stored the transformation in the HDF file as well, and in this case it happens to be identical. Okay, oops. All right, let me I'm just thinking about where I have an example where we won't see that. This is what happens when you don't practice in advance. Let's see. Okay, all right. I had this is from the official tutorial for the GMM, and that made use of Empire 10076, which was a complete ribosome data set, I think. Actually, maybe it's just a large sum unit or something like that. I think it's maybe some sort of depleted ribosome, but anyway, regardless. Okay, so what we have here is one of the new style EMAN2 refinements. So in the old style EMAN2 refinements, you'd have a folder called refine, followed by a number indicating which run it was. In this new style refinement, you get these R3D folders. So if we look in R3D06, we'll see a series of iterations here, but there's no class averages in this approach. And what we wind up with is a set of these LST files for each iteration. So let's take a look at one of these LST files. Okay, so it looks very similar to the LST file we were looking at before, although now you'll see that the file names aren't, I think, all the same. Yeah, you can see. So you can see here that the file names change now. In the other LST file we were looking at, basically there was just one stack file that had all the particles, and there was an LST file which had basically just pointed to the same images in the stack file. In this case, the LST file is combining data from a bunch of different image files. So if we look in the particles folder, similar to the folder that we're building now with that conversion tool that we have running in on the other screen. So the conversion that's running here, similar to that, we'll have a bunch of these individual micrograph based files here. So you can see when this project was refined, we did a refinement using the old style refinement. We also did refinements doing the new style refinement. We also did some 2D class averaging using the bispectrum based class averaging program, and some other stuff in this little project. Again, if we look at the R3D06 folder, at the LST files there, now if we do an E2 display, oops. It's kind of irritating. Yeah. And we look at the LST file info. You can see the LST file is referencing particles from a variety of different images. Make this a little wider so we can see it. So you can see this one is referencing something from this file, and if we move down a little bit more, you can see now it's on to a different file. But the file contains CTF information, which came from the original image file, from the HDF file. But we also have this transform.projection parameter, which came from the LST file instead. All right, let me go back to Python. That's what we were trying to do. Sorry if this is a little bit scattered. Let's see. Particles 03 even dot lst 30. Whatever. So we can read the LST file as if it were an image file, and it'll get all of the metadata correct. Get attribute dict. Okay, so there's all of the header information, which is this merging of the header information from the HDF file and the header information from the LST file. Now, there's another way we can access these LST files. There is a class that EMAN2 provides for parsing LST files and interacting with them directly. So if we treat this as an image like this, everything's fine. I can read all of the header information. But if I want to create a new LST file, which consists of this extra metadata plus, the original image reference and stuff like that, I don't want to just say write image with this, because then that's going to write the image data back to disk. I want to be able to just handle the metadata. So there's a class called LSX file. We'll call this LSX file. R3D06 particles 03 even.lst. And this will create an instance of a class, which will allow us to access the contents of the LST file itself, to manipulate the LST file. So it has a read method, and it has a read image method, and a read images method, and a write method. So when we're doing a write here, we're not actually writing any image data. We're just writing information about the file name that contains the original image, the number of the file in the original image, and then we can also pass in this dictionary of additional metadata. So if I just say something, if I say l.read5, what we'll get back is the particle number, the file which contains the original image, and then here we get back just the extra metadata that was stored in the LST file. I could also just say L5 like that. Okay, so I can access these LST files in a very convenient interface, basically like it was a Python list object. A similar mechanism exists for JSON files. So if we look in this info folder again, we can see, for example, here we've got a JSON file for a particular micrograph. Story about the cat. And we can say J is equal to JS open dict info. Oops. Copy paste didn't work right. Still didn't work right. Sometimes with my VNC sessions, the copy paste stops working. Let's try that now. Let's try that. No. All right, I guess I will have to type it out. Fine. L17. Combine. Info.json. Okay, and now J is going to be one of these JSON dict objects. And if I say j.keys, I can see all of the metadata that's stored in that JSON file. So I could say J of CTF, for example, and I can get back the CTF object. Sorry, there's a lot of information about in the CTF object. Or I can get information about the quality or the sets or whatever. I can get out all the information about that particular micrograph easily. I could also manipulate the dictionary. If I wanted to add some new metadata item, I could say J of my data is equal to 120, something like that. And that would actually modify the contents of the JSON file. I don't want to do that in this case, but it wouldn't hurt anything, but I don't want to actually modify it. Right. So we have an object type for interacting with these LST files. We have an object type for interacting with JSON files. There is actually also an object type associated with dealing with star files, although it's not maybe as complete as it needs to be at this point. I know the guys who are developing Spire were moving more towards a pure star-based representation for their data. So I think they may have developed something which is a little bit more complete. But there is a Pythonic star interacting object available here as well. If we look at, let me see if this is done yet. Almost done. So if we look at that conversion program, no, let's do this. Yeah, so if we look at that source file, we can actually see how it's dealing with the star file. Let's see. I'm going to assume that when Muon wrote this, he actually used the existing star parsing object. All right, I'm not sure where he did it. Maybe he. Oh, I see. I see. Okay, here. Okay, you can see here. Here's where he's defining he's made a little translation dictionary, I guess, because he didn't like typing this. So he made a little translation dictionary for the Relion header names into shorter versions of the names. All right, it looks to me like he actually decided to parse the star file himself rather than using the existing star file parsing algorithm. All right, let's see what we can do. Maybe this, if this is done, okay, if this is done, we can try it here. And I just have to remember what it's called. All right, I may have to search for it. I haven't used it in a while. Oh, actually, wait, the other Relion conversion program, I'm sure it uses it. Let's look at that one. Oh, it's just the EMAN. Okay. Okay. All right. So here's the old star file converter, and star. Yeah. Right. So here's the class star file. So basically, you just say star equals star file. So you open the file, and then once you do that, it basically gives you a dictionary access to any of the columns that are present in the file. So you say star of Relion type, it omits the initial underscore, but other than that, basically you just access it like a dictionary, and the dictionary, if you do this, it'll give you a list which contains all of the values for that particular column of the file. Okay, so now that this finished running, you can see that we wound up with a folder called particles, which is going to be basically the same as the file that we got in here called particles. And we wound up with an LST file, which It was written to a folder in a folder called sets, right? Because normally EMAN keeps its LST files in either in a sets folder or in an individual refinement folder. So if we look at sets, we can see all Relion.lst. So let's make a new EMAN2 folder, and we'll move particles and sets into EMAN2. Okay, so you can see that the LST file here, for each individual particle, it put the transform information, the orientation information for each particle into the LST file. The information about the defocus and that sort of thing would have been stored in the image headers. Where am I? Let me go here where I can do a GUI interface. Okay, so here's the folder we just created. We do E2 display. And if we look at particles, we will see this massive list of, a large number of particle images. If we pick one of these, info, we can see all the header data, which was stored for this particle. And we can see that it has the CTF information that came from the star file. And all the other parameter information. So really the only parameter information that was stored in the LST file was the orientation information, which is something that would change if we ran further refinements on the data. But we're going to assume that the defocus parameters and stuff like that aren't normally going to change. Now, if you did a refinement using the new 3D refinement program, it would produce a new LST file for each iteration. And those LST files might also include defocus information, because there is an option to refine defocus while you're running. Okay, so now what we should be able to do, although I think I'm not going to try and do it right now because it's going to take a little while to run with this many particles in it, is we should be able to just do a make 3D on this Relion LST file and do an EMAN reconstruction of the Relion, using the Relion orientation, CTF, et cetera, parameters, and get a 3D structure out. And that's something that we're going to need when we try to run the Gaussian mixture model. So I've talked for like an hour now about metadata and kind of strategies for metadata access and that sort of thing. But really all we actually did today was downloaded the Empire data and then ran this examples E2 convert Relion on the star file. From a productive standpoint, all we've done today is run that program and then produced these files. And then these files are what we're going to use next week. Like I said, sometime before next week, what I'm going to do is I'm going to combine this set of information, these images with the images from the closed data set. So we have one mixed population data set. And then I'll put those somewhere where you can download them. Yeah, we've been going over an hour, so I'm not going to go too much longer today. Maybe I'll just make one last interesting point related to sort of the data compression paper. So the raw data from micrographs, raw particle data, compresses pretty well with the strategies outlined in that paper, but it's about a factor of 4, and that's great. I mean, a factor of 4 less disk space for your raw particle data is obviously very useful. Certain types of files, like 3D volumes, which are generally masked, compress even better than that. So one of the other things I downloaded here were the open and closed mask files from this project. And I just thought I'd point out that if you run E2proc 3D on this, so this is currently 186 megabytes. So if we run e2proc 3D on mask 360 open, and we'll call it x.hdf, and I'm going to put a :8 on there to say that we want to preserve 8 bits of precision on the mask. The compressed mask file is actually only 1.5 megabytes. So it's about a factor of 100 smaller. And the nice thing about that is this file you could send by email. This file you would have to arrange for some sort of file transfer to transfer. So if you're trying to send sort of final volumes that you got out of a reconstruction or something like that to someone else you want to look at, just converting it to HDF will generally save a tremendous amount of space. This isn't just masks that it's good for. You can also compress here. Let's take a look at a 3D refinement. Go back to the GMM folder we were in. Oops. Okay, back where we were. So if we look at the this 3D file here, you can see it's about 6.4 megabytes. If we convert that to an MRC format, so what you would see if you got it out of Relion, you can see that it was 131 megabytes. So this is actually an extremely useful size, disk space saving tool, which means that you can then basically keep all of these sort of intermediate files that you otherwise might have decided you wanted to throw out to preserve disk space. And if you email that to someone and then they say, oh, I don't have EMAN to look at it, I want to look at it in something else. Well, Chimera can directly read the HDF file, so you wouldn't have to convert it for that. And if you need to convert it back to MRC, well, as long as they have EMAN2 installed on the machine, they can just run e2proc 3D and convert it back to an MRC on the other end. Anyway, okay, that was a little bit of a rambling discussion about metadata today. I think next week we will be a little more task focused, and I'm going to try and sort of take you through the GMM process, and hopefully everyone will be kind of following along as we do that instead of this kind of lecture style meeting from today. Does anyone have any questions they want to ask about all that material I spewed out today?
I have a couple of questions and a comment.
Yep.
So comment is, as one of the Spire people, how the star processing stuff works is it treats the star file as a pandas object, if anyone's familiar.
It treats the star file as what?
A pandas data frame.
Pandas data frame. Okay. Yeah. Okay. That makes a lot of sense.
I don't know how if I would consider it like full featured or not, but it's useful. I actually.
So how does it handle the new style star files that have multiple loops in a single file?
Yeah, so they're separate data blocks. I don't remember if that's the right term in pandas. But
so you get multiple frames out or something, basically?
Yeah, so there'll be like a data block for optics and a data block for particles, for example.
Okay. All right. Yeah, that's good. That's useful.
Yeah, and pandas is useful for other things too. So I'm looking at more. And so my questions. So you said that the LST files have to be fixed length. The record has to be fixed length.
Each line in the LST file is fixed length. So one of the options in the objects that use there basically you can write out a bunch of these things and then it'll reformat the file to make sure the length is correct.
So if you want to modify an LST file, like one entry, does that mean you have to modify all of them so that they are the same length?
Eventually, you have to modify all of them. If you're doing it from a programming perspective, you can modify a whole bunch of them, And then there's a normalization routine you call at the end, which will make sure all the lines have the same length.
So there's some sanity check to make sure.
Technically, there are sort of two related formats. There's the LST and there's the LSX. The LST file doesn't have fixed length lines, and the LSX file does have fixed length lines. So even if the line length isn't fixed, you can still read them. It just gets extremely slow because every image, then has to seek to the correct point in the file. So basically they get sort of temporarily written as LST files, and at the very end you just make one pass through and you renormalize them to the line lengths.
Okay. And my second question is, for something like a class average, how would you encode an LST file from that? Because like the members of particles that belong to a class can vary wildly. So would you point to a JSON file, or how would you do that?
No. So so that metadata that's stored in the LST files is basically a JSON block.
So I mean, if you have to maintain the same length for all lines in the file, so like one class may have 0 particles and another one may have 10,000 particles.
Sure. No, that's right.
Oh.
So yeah, you're correct that it might that might result in having a very long line length and being kind of wasteful space-wise if you had a tremendous disparity between class membership and you were trying to put that kind of information there, but it would work still.
Okay.
I mean, you could come up with some edge conditions where that might not be the most efficient way of handling it.
Okay.
There aren't any current use cases
with
where
JSON file that has like the class members in it, for example.
So sorry, what did you say?
I was thinking that maybe you could like point to a JSON file that can be a variable length record and have
So the JSON files have always been variable length.
Yeah, but like point to the JSON file from the LST file.
Oh, sure. You could certainly do that. So if you're storing a bunch of class averages, the class averages would be generally stored in an HDF file themselves. And once you have a class average, the membership of that class average wouldn't be changing. So that would be a parameter I would normally store directly in the header in the HDF file. You don't need to use this LST mechanism for that. The LST mechanism is a way of sort of overriding the header data for cases where it's variable, where it's going to change over time, right? So for the case of class averages, it really wouldn't make much sense to use an LST representation in the first place. You just put it directly in the header, and the HDF format already deals with the variable sized header stuff itself internally. So there's no waste when you do it that way.
Okay, cool. Thanks.
Yeah. Okay. Anyone else? Anything before we cut it off for the day? All right. So next week we'll try and do something that's actually kind of more practical. I will try and get the data pre-processed so everyone can download it, a few days in advance and send out the information, so people have time to actually let the download finish. But otherwise, I think we'll call it for the week.
Seems like your cat has an hour attention span.
The cat will continue to sit there and say, "Hey, come over here and pet me," until I come over and pet him. He's 14 now, 15 now, 16 now. He's pretty old, so he's infinitely ornery and infinitely patient. Okay, bye everyone. I will see you all next week.